Hi again, my name is Manolis. I'm from Libre Space Foundation, a non-profit organization in Greece. Actually, we are a team of space enthusiast freaks, and we use SDR as our main way to communicate with satellites or other stuff that we do. So, our main project is SatNOX. SatNOX is a network of ground stations that track mainly low Earth orbit satellites. For those who are not familiar with low Earth orbit satellites, they spin in a high velocity around the Earth in about 400 kilometers above the surface of the sea. So you have to track them and to compensate the Doppler shift that is there. So another very interesting feature of our ground station is that we have a network of them. So because you do not have so much time to track it, it's about 15, max 20 minutes, you lose a line of sight with a satellite, so you lose the signal, of course. But another ground station in another place in the Earth can continue and track it. So this is our concept and what we are trying to do. Our tracker costs about 300 to 500 euros, depending on the SDR that you want to use. And we now support about 6 or 7 different SDR devices. So this is a tracker. It's completely open source and open hardware. All the schematics are available on our repository on GitLab. It is many of the parts are 3D printed, and all the others are very easily available in the market. So they are cheap, and you can build it for yourself. So it is crowdsourced. Of course, every operator who wants to enter the SatNOX project build his own tracker, and he registered it in the network. So until now, all the available software that is out there, it is used in Windows, and of course most of them are closed source, and are targeting only specific missions or satellites. Another very common problem with this software is that you cannot parameterize them. They are black boxes and they are operating for a single purpose. So what we do, we provide GNU-ready decoders for a large family of low orbit satellites, and we give the operator the ability to choose whatever SDR hardware he's willing to pay. So most of ground stations right now, they are using the cheap RTL SDRs with a simple LNA in front to get the signal properly. We provide all the web services, so the data that each ground station downloads, they get uploaded automatically on the web for further visualization. Or we have an API, so everyone can write some scripts to grab data for a specific satellite in a specific time instance also. So from last year, FOSDEM, it was a very, very busy year for us. We had the APSAT launch in space, which was our satellite. I will talk about it in a few slides. We do some very serious hardware and software improvements in the rotator. And also, as we were growing up, our web infrastructures were completely fried. So we have to update them as well. Also, we were involved with high-power rocketry for the CANSAT project. CANSAT project is an educational contest that students are launching small satellites inside the amateur rocket in about 1 kilometer height, and then the parachute deploys and goes down to the Earth. But the high power rocketry part and the telemetry of the rocket was our project. And in November we also contributed to the organization of the open source CubeSat workshop with ESA. So what is AppSat? AppSat is the first open source, completely open source and open hardware CubeSat. It was part of the QB50 project. The contributor of this project was the Von Karman Institute, and it was designed to measure the plasma concentration on the ionosphere of the Earth. It was developed by Libre Space Foundation together with the University of Padua. So we tried to use as much as possible free software. So for example, the PCB designs were designed in KiCad, the structural and the mechanical designs were designed in FreeCAD, and all of the designs and the code is available on our GitLab repository. And at April, using an Atlas V rocket and a resupply mission to the ISS, the satellite traveled to the International Space Station, where the astronauts took it. It was placed in a launch tube with a spring behind it. The ports open, and the first one is actually us, is the AppSat satellite, and it was jettisoned into space. You can see the massive panels of ISS here. So just after 30 minutes, we were able to receive our telemetry by SatNOX ground station in USA. So this is actually a very good example of the benefits of a network ground station around the globe. And see, here you can see a CW signal, and there are also some FSK frames that were decoded. And as I told before, high power rocketry was another project of LSF. We designed this board that has some sensors on it about g-forces, the velocity, has a GPS sensor, temperature sensor, and uses FSK to transmit back to Earth data. The decoder was completely based on GNU radio. So this is a waterfall of the first launch that we actually do, and we missed it. We didn't manage to decode frames during the flight. If you see here, it's a strange phenomenon. The g-forces actually did damage to the telemetry board, and we had a frequency drift. We had a very steep filter in order to receive it, and the frequency drift caused the signal to go outside this spectrum region, and we get no data. So this is a team that struggles to find the problem. But using the radio, we have stored the IQ, the whole IQ of the flight. So by plotting the waterfall, it was very easy to see that it was a drift. So we just relaxed the low pass filter that we had, and after that, at the second, third, and fourth launch, we were okay, and we get telemetry data. So during this year, we have some significant improvements in our SatNOX infrastructure, and we managed to parameterize completely all the flow graphs in order to support all the different SDR devices. So we have made a database with some good and known values, for example, for the gain, for the sampling rate, for each device, for the USRPs, for the AirSpy, for the RTL. And when a flow graph is executed on the Raspberry that runs that has each that runs on each ground station. The flow graph takes automatically the SDR device that it uses and applies a proper configuration regarding the gain and so on. But because we have some operators that they use, for example, LNAs or amplifiers, we allow, of course, each of these parameters to be overridden by command line arguments. For every observation, we store the IQ, and then we generate a flow waterfall. We convert it to PNG, and this waterfall image is uploaded to our network. And if the satellite that we are targeting is supported, we choose one of the available real-time decoders in order to decode data. If the decoded data are successfully pass some criteria, like for example CRC if it's available, or it has meaningful data, it also gets uploaded into the network. So what we have right now as far the automatic decoder concerns, we have a CW decoder, which actually is a Morse code decoder. FSK, FSK 1200, it's a very common in space missions. APT, it's the NOAA image satellites, weather satellites, sorry. FSK 9600. DAV, which is very interesting, is data under voice. It is used in AMSAT satellites. They have some kind of FM transponders to allow amateur operators to speak it to each other, and they have a very slow speed telemetry transponder below the FM the voice. So I think that it is 300 Hz, from 0 to 300 Hz, and it is using 8B, 10B encoding. And we have right now under development the LRPT, which is also a weather satellite that uses digital imaging, and some PSK31 decoders that I believe in a couple of months it will be ready. So all the decoders are available under the apps directory of the GR Sandbox out of 3 modules. You can go and check them and play with them. So some words about the CW. Surprisingly to me, I didn't find any GNU radio based decoder. So I started to experiment with one. It was quite hard, I can say, because to me that I was coming from digital signal processing and digital telecommunication standards. I didn't have perhaps expertise, but with enough experimentation, I ended up using a PLL-based solution. So I filter the spectrum, and the CW is just a sign that goes on and off. And using a PLL, the PLL automatically shifts this sign into the DC. So you there apply a very steep low-pass filter, and after doing the mag squared of the signal, you can decide if you have a tone or you have absence of tone. So it works pretty well, I can say. The problem is that the very steep filtering that you have to apply in this part requires more CPU resources. So the trick is to just perform decimation in many stages, and you're okay. You can run this decoder without a problem in the Raspberry Pi. Another interesting decoder is the automatic picture transmission decoder. It's an analog transmission scheme. It uses signals from the NOAA weather satellites that orbiting the Earth in a polar orbit. It is AM over FM or at the VHF band, and you can see the spectrum in the left and the resulting image on the right. We use some synchronization patterns that this image has to synchronize the image and get it properly in place. So about the AX.25 FSK, as you can see, we also automatically decode this scheme. Hopefully this packet mode has a CRC, so we can check if the data are well decoded, and if yes, we upload the binary data into our network for further visualization. In the same manner, there is a FSK, the lower bitrate FSK. Unfortunately, it has not scrambling, so it's a bit harder to decode properly, and it has a very poor training sequence. So our main problem here was to get rid of the false alarms. We get too many false alarms because of the 1 byte synchronization sequence that it has in front. And then we ended up, the problem was to reduce these false alarms because we miss the frames, and the problem is that you cannot apply energy detection techniques, especially in our case, because every operator uses its own SDR device, it has its own RF setup. So somehow we needed to find a way that it is not affected by all these parameters. So the solution came with the idea of observing the quadrature demodulated signal, and when there is noise, the quadrature demodulation block generates a very noisy signal, of course. But when there is signal, the quadrature demodulation output is more structured. So by continuously measuring the mean and the variance of the signal, you can decide if it is signal free or with actual signal. So to give you an idea how important this filtering is, I have a flow graph. Yes. Okay. This is the decoder for the Fox 1B and 1D satellite, and I will try to execute it without the filtering. Yes. So these tags on the blue signal is actually the false alarms, because it has only 1 byte of frame synchronization word. It is triggering too many false alarms in the quadrature demodulated signal. The red one is the output of our filter. So if you see, when the signal is more structured, because actually the satellite transmits, the blue signals comes out of the block, and we can further processing. So right now I will disable the okay. on the best analysis. Yeah. So you can see no false alarms, and when the red signal comes, you can see some tags indicating the start and the end of the frame. Another advantage of this filter is that you're blocking the next decoder, so you get you spare some CPU by doing this. So this filter can be used on every FSK, MSK modulator. So if any one of you have the same problem, just go and grab the code. So, what are the real challenges that we face? We have found ourselves that it is very, very difficult to apply filtering on, especially on small factor PCs like the Raspberry, and there is still poor SIMD support. So we have tried to use the Pine 64, for example, or the Tinkerboard that has some better neon instructions, but we haven't yet managed to visualize the results in terms of performance and CPU utilization. Also, a very big problem, especially in the Raspberry Pi, is the USB communication with the SDR. For example, we cannot get in real-time samples from the SPI, and the CPU utilization. Actually, I think that I have seen that the CPU is a bottleneck there. One core gets 100%. Another very common problem with us is the low SNR. Satellite signals has very low SNR, and it is very hard to detect frames in the signal. So if you want to be more accurate or more to apply more deep searching on the signal, the CPU goes completely crazy in the Raspberry. So we have to keep our detection algorithms very, very simple. Another great problem is the lack of framing information. Satellite operators, for some strange reasons, do not publish their frame information, so we cannot easily detect them. In most cases, this is done by hand and by the eye. So we get the IQ and we demodulate it with the quadrature demodulation block, and we try to analyze the resulting bit stream. And of course, another problem is that we do not have any kind of IQ information. It is very, very helpful to have an IQ and apply your algorithms in order to decode it. But for now, there is not such a database. We plan to build one. So right now we store the signal of capture in an audio way. So we convert back down to audio, and we upload it to the network. So our intention is to store it in the IQ format. But this has many problems. For example, storage may be an issue, or many of the operators do not want to spend their bandwidth. So we are a bit skeptical about it, but audio format loses information. So if we want to go to the next step, we should store it in IQ format. So we have seen the CMF stuff and all the discussion about it, and we are willing to provide all the necessary storage, but we are a small team, so if some of the CMF community wants to contribute and apply their CMF some kind of CMF integration in our network, we will be glad to cooperate. So if you are interested, just talk with us. And another very interesting feature that we want to apply is the AX25 forwarding of the packets, because Linux kernel has its own module that can IP forward this kind of packets. So, for example, an operator can has a listener in a server, and when we get AX25 packets, we automatically forward to it. So it will be very helpful for the community. And last but not least, sorry, we believe that SDR can drive the next big space thing. Using SDR, we have managed to track satellites, to command satellites, to get telemetry from rockets. So it is a very good tool, and it drastically reduces the cost of a mission. Believe me, when we were debugging our satellite, if we have not an SDR expertise, our budget will be 10,000 above it. We spoke with teams that did not have the SDR expertise, and they were buying very expensive equipment just for sending FSK or getting the spectrum of FSK, which is ridiculous. So this all for me. If you are interested, go to the Libre Space Foundation repository on GitLab, get the code, see the code, comment us, or whatever you want. So, thank you.
Yeah, we can probably squeeze in one question, like considering the video switchover thing. Yes. Any questions? So okay, I have one. Like,
yeah.
Can you like, so how many people are the Libre Space Foundation, and like what's like the funding?
Most
model?
of them are right there.
Can you raise your hand? Can you raise your hand? Okay, so.
We're about 10 to 12.
Nuked right now, the Libre Space Foundation. Okay, but like you're a small group, and like what about funding? Is that like?
The initial funding was after a Hacker Day prize that we won a couple of years ago by applying in a contest with the tracker and the whole SDR stuff. So that was the initial funding, and then the AppSat project came, and all of this, nothing else.
Okay, well, thank you again.
Thank you.